Hey everyone, and welcome back to the deep dive. You know how we always say we're diving into the stuff you're actually interested in? Well, this time we're tackling how scientists are using deep learning to measure all those crazy shifts and changes happening on Earth.
Right.
From glaciers
Right.
to earthquakes
Yeah.
and even volcanoes,
Yeah.
the really cool stuff. And the jumping off point for this deep dive is a research article
Okay.
called Ground Surface Displacement Measurement from SAR Imagery using deep learning.
Sounds pretty dense.
It is, but
Yeah.
that's why we're here, to break it down.
Absolutely.
So before we even get to the deep learning bit,
Yeah.
what even is SAR imagery?
SAR stands for synthetic aperture radar.
Okay.
And basically, it's a way to create images of Earth's surface using radar signals from satellites.
From space?
Yeah. And the best part is it can see through clouds and work at night.
Whoa, so it's like having X-ray vision for the planet.
Exactly.
That's so cool.
Yeah.
But before we get to all the fancy deep learning stuff,
Mm.
how have scientists traditionally measured these ground displacements?
Well, there are two main methods. The first one is called INSAR, which is short for interferometric SAR.
Gotcha.
And that method uses the phase information from radar signals to detect teeny tiny changes in the ground's elevation.
Huh.
Think of it kind of like looking at the interference patterns you see when two waves meet.
Okay, I think I get that.
Yeah.
What's the second method?
So the second method is called offset tracking. And instead of phase like INSAR, this one focuses on the amplitude of the radar signals. So by comparing images taken at different times, scientists can actually see how features on the ground have shifted.
Oh, so it's like playing a cosmic game of spot the difference.
You got it.
I like that.
Yeah.
But these methods got to have some limitations, right?
Oh, absolutely. INSAR can get messed up by things like changes in vegetation or even like atmospheric conditions,
Okay.
and that leads to what's called coherence loss.
Coherence loss.
Yeah, it basically means the images get too blurry to compare accurately.
Nonsense.
And then offset tracking, while super powerful, requires a ton of computing power.
I bet.
We're talking about analyzing huge amounts of data here. Imagine trying to track tiny shifts in the ground over like a massive area.
Yeah, that's got to be a nightmare.
It's mind-boggling.
So this is where the deep learning comes in.
Exactly.
This research team decided to go a totally different route.
Yeah, they wanted to see if they could train a deep learning model to predict those ground displacements, but from SAR images and almost instantly. Like, think about how valuable that would be.
Oh, wow, yeah.
Near real-time data on ground movement.
Huge for things like disaster response.
Totally, or even just general earth science research.
That's wild. But I'm curious, what kind of data did they actually use to train their model?
They use something called CSLC-S1 data.
CSLC-S1 data.
It stands for Co-Registered Single-Look Complex Data. It comes from the Sentinel-1 satellite mission, and these pictures are already geometrically corrected, and they come in these bursts that cover specific areas. For their training, they decided to focus on Alaska.
Alaska.
Mm-hmm.
Seems a good choice since there's so many glaciers there.
Oh, yeah. It was definitely strategic. Glaciers are a perfect training ground because they have this consistent and measurable movement.
Sure.
Plus, since they were looking at Alaska, they had a ton of data to work with.
How much were we talking?
Over 200,000 pairs of SAR pictures.
Wow, that's a lot of pictures.
Yeah.
You've mentioned this deep learning model a couple of times. What is it called? How does it actually work?
They call it CC-resiumness.
CC-resiumness.
Yeah. I know it sounds kind of complicated,
It does.
but it makes sense when you break it down.
Okay.
It combines elements of two really powerful architectures, UNet and ResNet, and those work together to learn those complex patterns in the SAR imagery.
So they basically took the best of both worlds and mashed them together.
Exactly.
I can't imagine it was easy training this model.
Oh, no, it wasn't like teaching a dog a new trick.
Right.
They had to get creative and use something called iterative training. Basically, they broke the data down into smaller chunks and trained the model in stages.
Right.
And that let them overcome the memory limitations they were running into.
So it was like training it bit by bit.
Exactly. But the really cool part is once it was trained, the model could generate these things called offset maps from thousands of image pairs in just minutes.
Hold on. Minutes.
Minutes versus hours or even days with the traditional methods.
That's incredible. That's a crazy time saver. But the big question I have is, this model was trained on glaciers. Can it work for other types of ground displacements too?
Right.
Like what about earthquakes or volcanoes?
Well, that's exactly what the researchers wanted to figure out. They put their model to the test.
Okay.
And let's just say the results were a little surprising.
Oh, really? This is where it gets interesting. Tell me more.
All right, so
All right.
they tested it on all sorts of scenarios. glaciers in China and Chile,
Wow.
the Ridgecrest in Turkey earthquakes,
Girlies.
even the Tal and Mauna Loa volcanoes.
So they really put it through its paces. Did it work? Was it just a one-trick glacier pony? Or could it handle the other types of ground displacements too?
The results were actually pretty amazing. The model did really well across all the different scenarios,
Way.
even though it was only trained on glacier data.
That's wild. I would have thought it would need to be trained on each specific type of ground displacement
Yeah.
to be able to predict it accurately.
Yeah.
What did that tell us?
Well, it seems like this deep learning model is picking up on some of the fundamental principles of ground displacement,
Okay.
regardless of the actual cause.
Interesting.
So in each of the tests, the model was able to accurately identify the overall displacement patterns, things like the direction and magnitude of the movement.
So it could tell which way the ground was shifting and by how much.
Exactly.
That's pretty impressive.
Yeah.
Did it uncover any other details?
It gets even better. When they tested it on the earthquake data, the model was even able to pinpoint the ruptures. You know those breaks in the Earth's crust where the movement actually happened?
Oh, right. Okay. That's amazing. So this deep learning model sounds like it has a ton of potential. But I'm guessing even a super smart model like this has to have some limitations, right?
Yeah, of course.
What are the researchers saying about those? What were some of the challenges they ran into, and where do they see this tech going in the future?
One thing they were really upfront about was the need for more diverse training data.
Oh, yeah, that makes sense.
You know, right now, the model's accuracy is limited by what it's been exposed to. In this case, it was trained on tons of glacier data,
Right.
but not a lot of other types of ground movement.
So if we wanted to get even better at predicting things like landslides or even those tiny shifts in infrastructure you mentioned before,
Right.
we need to feed it more examples of those types of events.
Exactly. The more variety it sees during training, the better it'll be at recognizing and predicting all those different types of ground displacements in the real world. It's like expanding its vocabulary.
That makes sense. Anything else they think could improve it even further?
One really cool possibility they talked about was integrating other types of data.
Okay.
Right now, the model's only using SAR imagery as input.
Uh-huh.
But what if we could combine that with other information,
Like what?
like optical imagery, elevation data, or even weather patterns?
That's a great point. You could potentially get a way more complete picture of what's going on.
Exactly.
So now it's like there's a ton of potential here. Speaking of potential, we've talked a lot about this one specific model and the research behind it. But from your perspective, what's the big takeaway? Why is this research so important?
I think this deep dive really shows how depth learning isn't just some abstract concept that's stuck in computer science labs.
Right.
It's a powerful tool that can totally change how we study and understand our planet.
It's like taking all that super complex data and making it useful for solving real-world problems.
Exactly. And for ground displacement, the implications are massive. Think about it. Ground displacement is a key part of so many natural hazards.
Yeah, true.
Earthquakes, volcanic eruptions, landslides, all of that stuff involves movements of the Earth's surface.
So if we can get better at spotting these movements early on, we have a better chance of actually predicting those events right.
Right.
And maybe even lessen their impact.
Exactly. Imagine early warning systems for earthquakes or volcanoes that are way more accurate and faster than what we have now. We could potentially save tons of lives and reduce the damage from these events.
It's pretty amazing to think about. But it's not all about disaster response, is it? Didn't you say this tech could be used to monitor infrastructure too?
You got it. Things like bridges, dams, pipelines, all that can be affected by even the smallest shifts in the ground over time. If we can track those and spot problems before they become disasters, it would be a total game changer.
It'd be like going from reacting to problems after they happen to actually preventing them in the first place.
Okay.
That's huge for safety costs, even for sustainability.
Absolutely. And that's what's so cool about this research. We started talking about pixels in an image, and now we're talking about things that could have a real impact on people's lives.
It really shows how science, technology, and our everyday lives are all connected.
For sure. And there are so many exciting avenues to explore. What if we could use this to create early warning systems for landslides?
Wow.
Or to monitor how stable slopes are in areas where avalanches happen?
We could maybe even stop these tragedies from happening at all. Those are some big ideas.
Yeah.
You know, one thing that really struck me about this is that we already have mountains of SAR data just sitting there waiting to be analyzed.
Oh, yeah.
Decades worth of images showing all those little ground movements all over the planet.
Think about what we could learn if we used this deep learning tech on all that old data. We could track how climate change has affected glaciers over time, find fault lines we didn't even know were there, or even study those tiny ground movements that happen before volcanoes erupt.
It's like having a time machine for the Earth.
Exactly.
This has been a really incredible deep dive. Thank you so much for taking us on this journey and breaking down all this complicated science.
You're welcome.
For our listeners who want to dig deeper, we'll be sure to link to the full research article in the show notes, along with some other resources that might be helpful.
Definitely. The article's a really good read, even if you don't have a science background. The authors did a great job explaining it in a way that anyone can understand.
Totally. But for now, we'll leave you with this final thought. We can now measure ground displacements with incredible speed and accuracy, which was unthinkable just a few years ago.
Yeah.
The possibilities are truly endless. What will we do with this knowledge? How can we use it to understand and protect our planet better? It's up to all of us to keep asking these questions, exploring and pushing the boundaries of what's possible.
Well said. Until next time, keep being curious and never stop learning.
And be sure to join us again for another deep dive into the amazing world of science and discovery.
Yeah, it really is mind-blowing. It's like this tech could help us create early warning systems that give us more time to prepare for disasters, build smarter infrastructure that can handle those tiny shifts in the ground,
Right.
even help us understand how our planet is changing and how we can protect it better.
And that's really just the beginning.
Yeah.
What we've talked about today is really just the tip of the iceberg. There's so much more to explore in this field. It's a pretty exciting time to be studying Earth science.
I can definitely feel that excitement. But before we wrap up, is there anything else that stood out to you about this research? Anything that left you with lingering questions or like those aha moments?
You know, what I found really fascinating is that we can use this deep learning to kind of go back in time.
Oh, yeah.
You know, we have all the SAR data collected over decades showing all those subtle ground movements all over the planet.
Right.
We could use these new deep learning models on that data.
And uncover all sorts of hidden patterns and trends.
It's like we'd have a window into the past. We could see how things have changed over time.
Exactly.
Maybe even find areas that were more active or prone to certain types of ground movement. That would be super valuable for understanding the long-term effects of things like climate change.
Absolutely. And it just shows that we're not only measuring ground displacement, but we're also uncovering clues about how the Earth works, how it's changed, and how it's constantly evolving.
This has been a truly amazing deep dive. Thank you so much for taking us on this journey and for explaining all this complicated stuff in such a clear and engaging way.
My pleasure.
For our listeners who are interested in learning more, we'll include a link to the research article in the show notes and some other resources that you might find helpful.
And the article itself is a really good read, even if you aren't a scientist. The authors did a great job of explaining everything so that anyone can understand it.
For sure. But for now, we'll leave you with this final thought. We now have the power to measure ground displacements with a level of speed and accuracy that was unimaginable just a few years ago. The possibilities are truly limitless. What will we do with this knowledge? How will we use it to better understand and protect our planet? It's up to all of us to keep asking those questions, keep exploring, and keep pushing the limits of what's possible.
Well said. Until next time, everyone, keep that curiosity alive and never stop learning.
And be sure to join us again for another deep dive into the fascinating world of science and discovery.